Now the third example I'd like to cover on applications of first-order differential equations is radioactive decay. And this follows closely with Greenberg's section 2.3.2. As you probably know, radioactive decay is used in, for example, as a technique of dating different materials. And so let's, in that context, let's discuss it. So say we have a material, a radioactive material, that has a mass m. And some examples of that radioactive material are, say, carbon-14, the carbon-14 isotope, uranium-238, or say, for example, thorium-234. The rate of decay of the mass is proportional to the amount of mass present. The rate of loss of m is proportional to the amount of material decaying. That should make sense. So the MDT, the rate of decay, the MDT is equal to, so it's negative because the mass is decreasing, and it's the constant of proportionality is the decay constant K, and then we have M. So the more mass there is, the more rapidly, then the larger number of grams per second are being lost. So this is the differential equation that governs our system. This is our this is a description of our conceptual model written formally as a differential equation. And this differential equation is even simpler than the other examples we discussed in that it's also in first order, but it's homogeneous because there are no terms that are completely independent of mass or its derivatives. If we were to put terms of mass and its derivatives on the left-hand side, the right-hand side would be 0. So the homogeneous equation is relatively easy to solve. We separate, in this case it's separable, so we can put all terms of m on the left-hand side of the equation and all terms of t or its differential on the right-hand side, and we can integrate. And when we do that, we get the log of m is equal to minus kt. The log of the absolute value of m is equal to minus k of t times c. And the solution gives m is equal to m naught. M naught is given by the constant times e to the minus kt. So m naught is the starting mass. That's our initial condition on mass. That is at t is equal to 0, whenever that may be. And in the context of dating, if we know what the mass is today, we know what the starting mass is, as well as the decay constant, we can determine how long this material has been decaying. So again, if we know the mass today, m at a given time, which would be today, the starting mass, as well as the decay constant, we can figure out T, the age of this material since it started decaying. So with that, that's relatively simple reasoning for this dating method. The slight detail is that usually K is expressed in terms of half-lives. And we'll use capital T for the half-life. And it's the time for half the material to decay. So we can write our equation in terms of our half-life. So we have m over m naught is equal to 1/2, and that's equal to, we've just divided both sides of our equation by m naught, and we have e to the minus k times t, and t again is our half-life. Okay, and from this we can solve for t, or solve for k in terms of t. And we get, we get k is equal to the natural log of 2 over t. So our solution in terms of the half-life is m is equal to m naught e to the minus natural log of 2 times t over capital T. And see, you'll note that we're raising e to the log of 2, and that gives m equals m naught 2 raised to the minus t over t power. And this is the solution for radioactive decay in terms of the half-life, and you can apply this for dating. And just to give some examples of half-lives, T is equal to about 5,500 years for C14, and this is useful for dating, say, the time of death of biologic materials. The idea being is that solar radiation of the atmosphere generates carbon-14, and that's a radioactive decay. So while an organism is living, it's breathing and eating this carbon-14, and it becomes part of their bodies. And it's continually being replenished by when it's alive, because it's continuously interacting with the atmosphere. But once it dies, there's no more carbon-14 being supplied to its body. And so with time, that carbon-14 decays, and using this equation, we can date the time of death, that is the time in which carbon-14 ceased to be supplied into its biological material. Another application, for example, is the radioactive half-life of, say, uranium-238, which is 4.68 billion years. And this is useful for dating old rocks. They have to be old rocks because the half-life for 238 is comparable to the age of the Earth itself. But nonetheless, we can use 238 to date rocks back into geologic time. Okay, so this concludes this video using the example of radioactive decay.